There's this one chemical that shows up in everything from the fertilizer in our fields to the fuel in our rockets. It's a real cornerstone of modern industry. Today, we're going to break down the surprisingly clever process used to create it, the making of nitric acid.
So, think about it. How do you actually make something that's known for being so powerful and reactive, but on a massive industrial scale? This stuff is essential for so many things, so you've got to get it right. Where do you even start?
Well, it turns out the answer lies in a process that was perfected more than 100 years ago, and it's still the best way we have to do it. It's really a masterclass in chemical engineering, a four-step journey that takes some of the most basic materials you can find and turns them into one of the world's most important assets.
Okay, but before we step onto the factory floor, so to speak, let's get properly introduced to the star of our show, nitric acid itself. What exactly is this stuff?
Its chemical formula is HNO3, and the two words you really want to remember here are strong and highly reactive. That reactivity is exactly what makes it so incredibly useful, but it also means the whole manufacturing process has to be unbelievably precise and controlled.
So this specific method we're going to walk through is called the Ostwald process. The best way to think of it is like a four-step blueprint, a recipe that's been fine-tuned over the decades to make nitric acid efficiently on a huge scale.
And here's our roadmap for the day. It all kicks off with a simple mix. Then, that mixture gets heated up and converted inside a reaction chamber. After that, the gases that come out are cooled and changed again, and then finally, they're absorbed in water to create the acid. So, let's jump into the details of Step 1. Our journey starts with the raw materials. Step 1 is all about creating the absolute perfect mix to feed into the system. Seriously, if you mess this part up, the whole thing just doesn't work. And the ingredients themselves are surprisingly simple. Just ammonia gas and, well, regular old air. These get piped into the system to start everything, but you can't just dump them in together. The ratio is the secret ingredient. And I mean this. Precision is everything. The ratio of ammonia to air has to be exactly 1:10. That's not a guideline. It's a non-negotiable rule for the chemistry to work. It's all about control from the very beginning.
All right, so with our perfect 1:10 mix ready to go, the gas is fed into Step 2, the catalyst chamber. You could really think of this as the heart of the entire operation. This is where the first huge transformation happens.
So what's going on in there? Well, the gas mixture flows over something called a platinum gauze, which acts as a catalyst. It basically just makes the reaction happen way, way faster. You need a little jolt of electric heat to get it started, and then, bam, the ammonia is converted into a brand new gas, nitric oxide.
Now, the most important word to understand here is exothermic. So what does that mean? It's simple, really. It means the reaction releases heat, and not just a little heat, a lot of it. And this right here is the genius of the Ostwald process. This is what makes the design so incredibly efficient. That little bit of electric heat we mentioned, that's just to get the party started. After that, the heat created by the reaction itself is more than enough to keep the whole process running continuously. It literally powers itself.
So, running on its own power, the chamber is now pumping out a steady stream of really, really hot nitric oxide gas. But to get to our final product, we need to cool it way down and let it transform one last time.
And just look at that temperature drop. The gas leaves the catalyst chamber at a scorching 750 degrees Celsius. It's immediately shot through cooling coils that bring the temperature crashing down to just 50 degrees. This super fast cool down is absolutely critical for what's about to happen next.
Okay, now that the gas is cool, it goes into an oxidation chamber. In here, the nitric oxide mixes with some of the leftover oxygen from the air we put in way back at the start. This triggers another reaction, and the gas changes again, this time into nitrogen dioxide. We're getting so close now.
And this is it, the final, elegant piece of the puzzle. The nitrogen dioxide gas is bubbled up through water inside a big absorption tower. As the gas, the water, and any leftover oxygen all react together, they rearrange themselves into our target molecule, HNO3, nitric acid.
And the result of all that is a solution of dilute nitric acid. It just trickles down to the bottom of the tower, where it's all collected. From that point, it can be stored, shipped out, or made even more concentrated for whatever it's going to be used for. And just like that, our factory tour is complete.
So we've seen the whole blueprint for turning simple ammonia and air into one of the most important chemicals in modern industry. We know how it's made. But that leaves us with an even bigger question, doesn't it? What does an acid this reactive actually do out in the real world?
What does it help us build, or create, or even discover? That's a thought to chew on.